Good afternoon, everyone. My name is Silvia, and I'm going to present to you the multi-camera monitoring system for object following and obstacle avoidance that I developed throughout the past few months. So in this presentation, I will start by explaining the context and motivation for this project, then talk about the multi-camera system setup and integration, move on to the object detection and following, and lastly, we will talk a little about obstacle avoidance. Before anything else, I think it is important to understand why do we need a multi-camera system in the first place. Looking at this image, we can easily understand the limitations of a single camera vision system. In this example, where we are trying to track 3 different people while they are in motion, we can understand that the performance of the system will be low, given that we can easily lose track of one or more of the people with a simple movement. To overcome this problem, which we refer as occlusion problems, we decided to develop a solution where we can use as much cameras as we consider necessary to assure the full coverage given the expected people and objects in a given environment. This will assure that there are no occlusions in the environment and will allow us to increase the performance in tasks like tracking or obstacle avoidance. So, how do we start? To achieve this, the first step was the camera SDK configuration and the parameter exploration to find the best trade-off possible between precision and performance, so that we are able to develop a system that is in real time, but at the same time we are able to assure some accuracy and precision in the movements that we are trying to track or the obstacles that we are trying to avoid. Afterwards, we proceeded to assure a way of acquiring parallel images of the multiple cameras. We decided that this could be achieved by recurring to the usage of threads. So basically, for each camera detected in the system, we are creating a new thread that will allow us to acquire the RGB images that we want in a given moment from all of the cameras at the same time. At this point, it was time to understand how to calibrate the multiple cameras, because we have cameras that are placed in a lot of different places, pointed at one center point, but we needed to understand how to put them all in the same reference frame. So we did a lot of research in this field. We looked for a lot of different methods, some based in 2D points, some based in point clouds, and we decided to use the iterative closest point algorithm. This algorithm is used to minimize the difference between 2 cloud points and basically consists of 3 main steps. In the first one, we find a correspondence of all the points in the source point cloud and try to find the correspondence in the target point cloud. Afterwards, we estimate the combination of rotation and translation using a root mean square point-to-point distant metric minimization technique, which allows us to get the best transformation matrix to align the source points with the matched points. This is an iterative system, as I explained, so we do this for as many iterations as we consider necessary. In the case of this solution, we used around 20 iterations. Afterwards, we have the matrix, so explaining this, that we did not do this with the entire point cloud because it would be way too expensive. So the way to extract this transformation matrix was basically to get some corresponding points from each of the cameras. So we extracted the RGB image, selected some points, some reference points in each of the images, and then we pass that to the algorithm so that it could work this process. Next, so this is not moving on. Okay. So in the thread that we created for real-time image acquisition for each camera, we extracted the 3D point clouds and the RGB images that I talked before, so that we could then apply open pose. In this image in the slide, we can see the final point cloud. This point cloud corresponds to basically all the point clouds extracted from the different cameras, transformed using the transformation matrix that we calculated using the ICP method. After this first stage is up and running, it's time to face the next challenge, how to process the data that we are acquiring in real time in order to allow real-time object following. In our case, we decided that the object we wanted to follow was the right-hand key point from a person in front of the camera. And so we decided to apply OpenPose in the multi-camera vision system. OpenPose is basically an open source library that allows us to detect key points from the body or some more detailed stuff. But in our case, we just wanted the key point. So we had to integrate the OpenPose with the solution developed in Python. And then we were already able to have a body key point extracted. These key points were in 2D, so we then had to convert that to the corresponding point in the 3D using the point cloud that we extracted. At this point, we already have the 3D point coordinates, but we still need to convert the coordinates from the camera reference frame to the UR5 robot reference frame. For this, we applied a similar technique to the one that I previously explained. So basically, we just put the robot in multiple positions and extracted the position using the UR5 robot controller. And then at the same time, we were acquiring with the reference camera system, we were acquiring the RGB image and we were extracting the exact same point in the image. We then applied the ECP method as I described before and were able to obtain the transformation matrix from the reference camera, that is basically camera 0, and the robot coordinate system. So after applying all of these transformations, we now are able to have one 3D point that corresponds to the position in the robot world. The next step, and because in our system we decided to use joint angles instead of passing the 3D points directly, was to implement forward and inverse kinematics for the UR5 arm. The forward kinematics equations are used to convert joint positions into the 3D point coordinates, whilst the inverse kinematics equation can be used to obtain the joint angles that allow the robotic arm to get to the desired 3 point that we chose, basically. So afterwards, we established the remote communication with the UR5 controller and started to use the real-time data processing flow to send real-time positions updates to the controller. We experienced a few different ways of passing this information in order to understand which ROS topic and which parameters were the best to allow a real-time smooth movement of the robotic arm. Here you can see the UR5 robotic arm following the person's right-hand movement. There are a little disclaimer, there are some times where it does not work that well because the Z camera finds some noise generated by the metallic robot arm. But in general, we can see that it follows almost in real time the person's movements. And we can just wait a little bit to see a few more of this video. We remember that the point that it's trying to follow is just the right hand, so the rest of the body could move and the robot wouldn't move if the right hand didn't move. And that is basically what we did for object following. For the obstacle avoidance component that was developed, we defined a circular trajectory for the UR arm to follow and used the right-hand key point coordinates as the obstacle to avoid. If an obstacle is detected at a certain time, basically what happens is that we calculate if the end effector new position will be inside that object influence radius. And if it is, we understand that we need to change the trajectory of the robot to avoid a collision. In these cases, to calculate the joint angles at each moment, we calculated the repulsive potential for each joint and multiplied it by the respective Jacobian matrix to obtain the final impedance calculation. This impedance is then added to the goal position that we had initially, And that is the sum of those two components is what is sent to the robot in order for it to avoid that collision. So thank you for your attention and for being here today. I would like to thank everyone at the lab that helped me throughout these months in one way or another, and especially to Liliana for helping me to understand a bit better the robotics universe. I am now open to answer any questions you might have about the work that I just presented.